Hello and welcome to the fourth webinar in our 2020 SAM webinars. I'm Doris Kite, and today I'll be presenting on batteries in SAM 2020 2.29 with a focus on battery technology. This is our webinar series for the year. We've already had an introduction of EV systems, and now this is the first of the battery webinars, which will focus on battery technology and the physical modeling. The next two webinars by my colleagues Brian and Paul will delve into depth for behind the meter and front of the meter systems. Register for free at sam.nrel.gov/events.html. Please note this webinar will be recorded and posted on the SAM website at sam.nrel.gov. For questions and answers, please use the questions box. The screenshots here show how to access that questions box. We will either type an answer to your question or answer it at the end of the presentation. So let's start with an introduction. On the left, you see there are three battery storage performance models. There's detailed PV battery, PV watts battery, and generic system battery. Detailed PV battery, shown on the left here, couples the full PV model with the full battery model. Similar to how the full PV model allows for detailed modeling of the components and system design, the full battery model allows for selection of different chemistries, electrical and thermal behavior, efficiency losses, and lifetime degradation. Also, there is much more flexibility in the dispatch modes. The PV and battery system can be AC or DC connected, where they share a hybrid inverter characterized by the selection on the inverter page. The PV watts battery couples the simplified PV model with the simplified battery model, which reduces the inputs to battery size, a generic lithium ion or lead acid type, and a dispatch option. This model is AC connected only. Finally, the generic system battery model models a generic power plant with a detailed battery model. It has most of the same battery modeling features as the detailed PV case, except that the battery can only be AC connected. Today I'll be using the detailed PV battery with commercial financial model. The primary battery modeling difference among the financial models are in the dispatch algorithms, which are the subjects of the two following SAM webinars. So for this focus on battery technology, these are our topics for today, ranging from a broad overview of how the model works, such as how are the battery properties represented in the component models, and which chemistries are available in our defaults, so that we can run a simple use case for a behind-the-meter storage application. Then we'll go a bit further into auxiliary features, such as our integration with REopt Lite for its battery sizing optimization, as well as how to calculate resilience metrics, such as the probability of surviving outages. Then we'll touch briefly on how a user can fit their own battery system from manufacturer data sheets, scientific literature, or collected data. Finally, we'll present recent updates to the battery model, as well as features that are upcoming with the new release for the end of this year. So the battery model works as a composition of individual component models with interdependencies among key variables such as state of charge, current, and temperature. Most of the component models are semi-empirical, equivalent circuit or reduced order models that allow detailed modeling of features important to PV battery system design and operation, and which do not require electrochemical knowledge or data. Instead, the models are flexible in that they can be fit using publicly available data from spec sheets, papers, or charts, or they can be used for modeling batteries with raw performance test data. Connections to the PV utility rate and cash flow calculator, among other SAM modules, allow for exploring performance-related metrics that cover a breadth of designs and applications. So similar to how the detailed PV model is based on modules strung together in series and parallel to form the system, the battery model starts with a single cell and its characteristics such as nominal capacity and voltage. These are used to build up a battery system with some power and capacity. The efficiency losses due to racking, hardware for monitoring, controls, and safety get swept up into a power converter section and charge limit section. The battery lifetime depends strongly on conditions under which the battery is operated, such as temperature, state of charge, total energy throughput, as well as the charge and discharge rates. While there is no universal battery lifetime model, studies often break up the fade mechanisms into calendar and cycling, which we follow in the lifetime model in SAM. The lifetime fade then affects the replacement of battery systems. The voltage curve is a function of the battery state of charge, operating current, resistance, and capacity. As batteries age, the resistance increases and the usable voltage range decreases. With higher currents, especially for lead-acid batteries, the voltage drops quicker, reducing the usable capacity. Temperature also plays an important role in the recoverable capacity loss. So the thermal behavior of the battery is modeled using a lumped parameter heat transfer equation that computes the temperature of the battery as a function of the ambient temperature and the operating current, which results in resistive heating. So let's turn to the SAM executable and look at the inputs to these models. I have open here a default PV battery commercial case. On the top, we have a selection of chemistries, which we'll go into more detail later. But here I have a nickel manganese cobalt oxide or NMC graphite lithium ion battery. The first box we see is battery bank sizing. So there's two ways that we can set the size of our battery bank using the capacity and voltage characteristics of the cell. So here the cell capacity is shown in the current and capacity box, and the nominal voltage of the cell is shown here in the cell nominal voltage. And we have a desired bank voltage. So we want the battery system to have a voltage of 500 volts. Those three values are used in this auto sizing feature. When we select a desired bank capacity of 20 kilowatt hours and a desired bank power of 10 kilowatts, we can see how the configuration is computed here. The result of our capacity and voltage is close, but not exact. We see that we have 139 cells in series. So each of the cells are connected in series until the voltage of the string is our desired voltage. And then strings are placed in parallel until our desired capacity is met. The max C rate of discharge and charge describes how quickly the battery can be operated. And this is the ratio between the desired bank power and the desired bank capacity. So we can have a max power of 10 kilowatts, and this means we can discharge the battery at that rate for 2 hours maximum. And that gives us our max C rate as C over 2. So then we can see that the max discharge power is 10 kilowatts, and then the max discharge current and charge currents is 20 amps. And we can operate at the maximum power for 2 hours. Alternatively, we can specify the cells ourselves. So I'll set the number of cells to be 139, so I have that nominal bank voltage of 500. And then I can increase my strings. I can also change my max C rate if I wanted to have a higher max charge and discharge current. But for now, I'm just going to use this auto sizing feature. You'll note that we have two ways to size the battery. The default is to use DC sizes, since batteries are sources of DC electricity. But if you're modeling an AC connected battery, the DC to AC conversion efficiency will be used to scale the battery size. So we'll get to this optimal sizing and dispatch from REopt in a later section. Next, we'll move on to power converters. So these are efficiency losses that are applied for both DC and AC connected systems due to the power electronics that are required. So for an AC connected system, the battery is connected to an inverter, which is then connected to the output of the PV inverter. Every time electricity flows across this inverter, there is some efficiency drop, which is modeled with these single values. And for a DC connected battery, there's a DC converter that is used to change the battery voltage to that of the PV voltage. And the net power from the PV and the battery is then fed through the shared hybrid inverter. So we have a DC to DC conversion efficiency, as well as an inverter efficiency cutoff. The DC connected battery stops charging or discharging once the inverter efficiency drops below this cutoff to prevent excess power losses. Next, we have the charge limits and priority. This captures some of the functionality of battery management systems as they maintain a safe and optimal operating window of current, temperature, and state of charge. And so we can choose some maximum and minimum state of charge, as well as enforce some minimum time at a charge state to prevent rapid cycling. The next section is the storage dispatch controller. So I won't go into much detail since the next two webinars will, but in general, there are 5 that you can see here. The first 2 are peak shaving, and this is an automated dispatch. The input grid power target uses a time series of maximum grid powers to be purchased. And then the input battery power target uses a time series of charge and discharge powers of the battery. And then the manual dispatch uses this schedule here, which you can then align with time of use or time of delivery schedules. So for our purposes, I'll just be using the automated peak shaving algorithm. So next we have the battery lifetime model. So the cycle degradation model determines how the battery capacity decreases with the number of charge and discharge cycles, whereas the optional calendar degradation determines how capacity decreases over time, regardless of cycling, and applies in addition to cycle degradation. So we have this simple lookup table for our NMC battery. Here, the effective capacity is the capacity percent compared to our nominal capacity at the beginning of life. The lookup table shows that this effective capacity is a function of the depth of discharge and the cycles elapsed. As the depth of discharge increases, the life fade increases. So we can see for the depth of discharge of 20%, we reach a capacity fade of 40% only after 10,000 cycles. But when our depth of discharge is 80%, we have an effective capacity of 60% or a fade of 40% after only 2,000 cycles. For the calendar degradation, there's two options. The first uses the lithium ion model. So here, the calendar degradation is a function of temperature and state of charge. As the temperature and the state of charge increases, the calendar degradation also increases, and here it's monotonically increasing. And we can adjust how the curves are spread out using some of these parameters here, which can also be fit using software outside. So this B parameter, for instance, has decreased the effect of temperature. And so that is one option. The other option is to use this custom degradation, in which case the effective capacity is only a function of the battery age. So the battery lifetime fade calculated is then an input to the replacement module. Replacements are useful to recover the battery capacity so that it can continue to meet its load. However, replacing the battery also requires replacement costs. So there are two ways to trigger replacements. The first is using the replace at specified capacity option, in which case you give it a percent capacity after which to replace 100% of its capacity. The second way uses a schedule. So this widget shows an array of years. If I want to replace a battery in year 8, I will enter a 1 in this row. And then in the replacement percent widget, I will then specify what percent I want to replace. In this case, I'll just say 100. Next, we have the battery voltage. So the battery bank voltage is calculated using the cell nominal voltage. The voltage curve that is drawn here is using this electrochemical model. This electrochemical model is a semi-empirical voltage model that splits up the voltage discharge curve of the battery into 3 zones. The first is this exponential zone, which is towards a 0 depth of discharge. When the battery is full, we see a sharp increase in the voltage. The second zone is this nominal zone, where the decrease in voltage is nearly linear. And finally, we have this steep reciprocal zone, where the voltage drops off really quickly. So this model can be used to fit a variety of voltage discharge curves. That's what these parameters are here. The first parameter is the C rate of the discharge curve. So it's the rate at which, it's the current at which this voltage discharge curve was tested. Next, we have the fully charged cell voltage. So it's the maximum voltage. And then we see the exponential zone cell voltage, as well as the charge removed at exponential point. This is the X and the Y coordinate of the end of the exponential zone, which is here. So it's about 4.05 volts with a depth of discharge of 1.78. So if I decrease this voltage, we'll see that it will result in a steeper decrease. And if I move the Y coordinate, we'll see that the exponential zone can extend further. and further. Next is the nominal zone cell voltage and the charge removed at nominal point. And this is the counterpart to the nominal zone, where we identify the X and Y coordinates where the nominal zone ends. So if I increase this nominal zone, we'll see much less decrease of the voltage during this nominal section. And we can also make a sharper drop-off by moving the Y coordinate of the nominal zone. So now this happens. Now this drop-off starts at 3.9. If I move this left, we see that this happens with a much longer for the reciprocal zone. The other option is using a voltage table, where you can specify the cell voltage as a function of the depth of discharge. And finally, the last parameter in this voltage model is the cell internal resistance. This parameter is also used in the thermal model. Next, we have battery losses. So these are used to specify additional hourly losses that are not captured by power conversion losses. These might include pumps, heaters, or other equipment required by the battery. So you can give kilowatt losses per mode on a monthly basis, or you can give a time series where these will be applied no matter the operating mode. The last component model is the thermal model. The battery thermal model assumes that the battery with specific heat capacity is in an environment at the specified environment temperature. Heat transfer between the battery and its environment is proportional to the heat transfer coefficient H. So some of the properties to this model is the specific heat capacity. For this NMC graphite battery, we have a 1500 joules per kilogram Kelvin value. This is 35% higher than the usual lithium ion 1000 joules per kilogram Kelvin. Because of the fact that we're modeling the thermal properties of the battery system, so containing the racking components and the battery management system and the extra space that would require. Next, the heat transfer coefficient H, value of 7.5 watts per meter squared Kelvin, corresponds to forced air convection with some impedance. An H value of 0 would be still air, perhaps, and an H value of 20 would be liquid cooling, which is available for some battery solutions. There are some ways to input the environment temperature as well. You can enter a single fixed temperature. So this is if the battery was in a tightly conditioned room where there's no variation in temperature. You can also use the weather file ambient temperature. And this is a battery that's outdoors and exposed to the ambient temperature. Or you can enter a time series temperature, which you may get as an output from a building energy simulation where the building maintains the room temperature of the battery within some set points. Other parameters needed for the thermal model is the battery mass and the battery surface area. So these are calculated using these multipliers, the specific energy per mass and the specific energy per volume. The specific energy per mass is the ratio of the battery capacity to its mass. And similarly, the specific energy per volume is the ratio of its capacity to its volume. You'll note here that these values are lower than you would find for NMC graphite cells. And again, this is because we are modeling the battery system, which takes up more space than just cells stacked on top of each other. And again, the resistance is another parameter to the thermal model, which affects how much resistive heating occurs due to the current flowing through the battery. So next we'll move on to what chemistries are modeled in SAM. Electric energy storage systems come in many types. Some fully mature, such as lead acid, and newer approaches, such as metal air batteries. We have three general chemistries that we model: lead acid, lithium ion, and redox flow batteries for vanadium or iron. Each of the types shares some, but not all, component models to capture the variation in performance you see in the graphs here. On the left, a comparison of the average specific power, energy density, specific energy, power density, efficiency, lifespan, and cycle life on a normalized and logarithmic scale for lead acid, lithium ion, and vanadium redox flow batteries. Of course, cost is another important factor, which isn't shown in the graph. But you can see that lithium ion performs well in its power and energy density, whereas the VRB has a higher cycle life on average. However, these are just averages, culled from a range of data points. This figure shows the range of performance collected by the same authors, which shows that there is significant overlap among the chemistries, which will depend on the model, operation, location, etc. And even among lithium-ion batteries, there's variation between different cathode and anode materials. In SAM, all the lithium-ion chemistries share the same components but have different parameters for voltage, life, and temperature. The graph on the right shows a comparison along specific energy, specific power, safety, cost, and lifespan, and cost metrics. While graphite, nickel manganese cobalt oxide, NMC, is an industry standard, LFP, lithium iron phosphate, and LMO-LTO, lithium manganese oxide, and lithium titanate oxide, are also well suited for renewable energy applications. So for lead acid batteries, there are three major types in SAM: flooded, gel, and absorbent gas mat, or AGM. I've listed some examples of these batteries that were used to define the battery default characteristics in SAM. The major lead acid specific feature is how the capacity of the battery depends on the operating current. The graph on the right shows a typical discharge curve as a function of discharge current. Puchert's law describes how as the C rate increases, the proportion of discharge hours to the expected capacity decreases, for which SAM uses the kinetic battery capacity model. For lithium-ion batteries, here's an example of an LFP, an LMO-LTO, and an NMC cell. All the lithium-ion chemistries share the same capacity, voltage, and lifetime models, but they have different parameters pulled from scientific papers and manufacturer data sheets. So the charts on the right are from the Sony LFP cell. The chart on the top shows how the voltage discharge curve is a function of current. Unlike for lead acid batteries, the discharge capacity doesn't depend much on the current, but there is a lower voltage, resulting in less area under the curve as less available energy. The graph on the bottom shows how the voltage curve changes with temperature, with reduced voltage and capacity at lower temperatures. While SAM won't model the variation in curve shapes as they deviate from the original exponential and nominal zone characteristics seen for the lowest temperatures, the loss in capacity is captured by the thermal model. For the vanadium redox flow model, there's an example of a UET reflex battery. And SAM uses the voltage model from D'Agostino in the paper shown on the right, where they fit the measured cell voltage from a testbed battery to an equivalent circuit model. This model has little degradation and thermal dependence, and you can use the ancillary losses to model pumps or other equipment. Now that we've seen how to define a battery system, we can run a simple use case for a behind-the-meter storage application and explore what performance metrics are available in SAM. So I'll be using the PV design in the default PV battery commercial case. It's going to be a 178 kilowatt AC system with an AC connected 20 kilowatt hour, 10 kilowatt battery. But I'm going to change the chemistry to LFP, and the dispatch option will be peak shaving. So we'll look at how does it affect the annual electricity bill, the payback period. What does the battery do over the lifetime? Do I need to replace it? Okay. So here we have the PV system as 179 and our battery storage. We'll switch this to LFP, and we'll look at this utility rate. We see that it has time of use periods for both energy and demand charges. And then when we look at the load, we see there's definitely a diurnal pattern and some variation in the peak on a monthly basis. So this means the peak shaving algorithm can try to level out these peaks and reduce our demand charges. So back to the battery storage page. We can see that some differences in the physical characteristics of LFP, which has lower energy density compared to NMC, but higher capacity or higher lifespan. So we can see that the calendar degradation is lower, as well as the cycle degradation. The voltage curve shows that the cell nominal voltage is about 3.2, and we have some capacity fade due to temperature. You'll see here that the specific energy multipliers are lower for this chemistry. So now we'll run simulate. And we can look at some battery metrics, such as a round trip efficiency of 90%, and 100% of the battery was charged from the system. And we have a payback period of 7 years. So we might be curious to see how the system would perform if there wasn't a battery. What we can do is duplicate this case and then change the model to a PV only case. This will preserve all of our PV system design. And then we can run a simulation. And we see that adding a battery has some benefit to our net present value and our simple payback. So let's look at some of the battery outputs. So we can look at the battery average depth of discharge over the analysis period. We see that it increases over time due to the decrease in capacity. You can see how the number of cycles increases pretty linearly over time. You can also see how the relative capacity of the battery to its nameplate capacity decreases with use. We can look at how the battery state of charge changes over time, as well as the total charge, where again, this decrease is due to the capacity fade. There's also outputs showing the power flow. And finally, we can look at how this battery is actually being operated. This shows the power discharged and charged from the battery over time. So the following webinars behind the meters and front of the meter systems will go more into depth on how to design and dispatch a system. So for now, I'd like to move on to some auxiliary features we've added, such as our integration with REopt Lite for its battery sizing optimization. The REopt Lite web tool is used for evaluating the economic viability of grid-connected PV, wind, and battery storage at a site. It's also used for identifying system sizes and battery dispatch strategies to minimize energy costs, and estimating how long a system can sustain critical load during a grid outage. So that is this option here. So I'm going to just get this call started while I explain it, because it does take several minutes to run. So we've integrated their battery sizing and dispatch strategy optimization to maximize net present value of the system. Since REopt Lite is designed for commercial building managers, this sizing feature uses utility rates to help reduce electricity bills. And so in SAM, this feature is only available for behind-the-meter distributed financial models, such as residential, commercial, and third-party. The way to use the optimal sizing feature is to determine the latitude and longitude of the location, set up the PV system, set up the load, select a utility rate, adjust the battery capital and O&M costs, adjust the value of loss load, and then click the optimal, and then click the get size and dispatch button. So while we wait for this to retrieve the results, I am going to, whoops. Let's restart that. Okay, so what I meant to do was to open a new instance of SAM so that we can walk through the steps. So the first step is to set our latitude and longitude. SAM will read the latitude and the longitude from the weather file. REopt will download its own weather file using the latitude and longitude, and cannot use the weather file from your SAM weather file library. Next, we'll have to set up the module and the inverter and the system design. We will pass the DC to AC ratio, as well as the total AC capacity to REopt, as well as some of the system parameters, such as the tracking mode and the tilt and the azimuth and GCR. Also, the losses from the losses page will also be inputs to the REopt optimal sizing. So next we will need to do the load. So the load can be input using this widget here. Finally, the electricity rate is also important. since REopt will be optimizing for the system's NPV and trying to shift the energy charges and minimize the demand charges. And so we can use this OpenEI US utility rate database download to search for rates. So for instance, I can type in a zip code and select a utility rate to download and to apply. Other inputs, yes.
Sorry to interrupt. There was a question about those electricity rates with REopt and whether the REopt integration can work with international rates.
I think the REopt Lite tool is using this utility rate database, which I don't believe has international rates.
So does the REopt, when you run the REopt integration with SAM, does it use the rate data from the SAM inputs, or does it look up the rate data on its own based on the?
Oh, thank you. Yes, it uses the data from the SAM GUI. So you can design your energy charges and demand charges and other parameters on this page, and everything will be formatted to this to the REopt format. So you can use custom rates that represent international rates.
Thank you.
Thank you, Paul. So another set of inputs to the optimal sizing functionality is the costs. So the battery costs are multipliers in dollars per kilowatt hour and dollars per kilowatt. And this will help REopt decide how to make the trade-off between a bigger battery and having more electric bill savings. Likewise, the battery replacement cost helps determine how much to cycle versus not to replace. And financial parameters are also used, such as the inflation rate, the discount rates, tax rates, and as are the incentives. So there are some incentives for storage, which you can input into SAM here, and these will then be used as inputs to REopt. So for the battery storage, there's also a value of lost load during outage value, and this just helps quantify the importance of meeting that critical load. And finally, when we click the Get Size and Dispatch, we will send this information to the REopt API, and as it does its computations, SAM will be polling for a result. As I mentioned, this could take anywhere from 3 to 5 minutes. So while we wait, I think I'll just move on to our next section, which is resilience metrics. So another feature in the SAM PV battery model is the resilience metrics calculations. These metrics are calculated by simulating an outage at every time step and calculating how long the load is met using just the PV battery system. So we have a min, max, and average hours of autonomy. We have average critical loads, the probability and cumulative distribution functions of autonomous hours, as well as the survival function of autonomous hours, which is plotted on the right, and the hours of autonomy during outage at each time step. So we'll set up a PV battery system, set up the load and critical load, and then click Simulate to see these metrics. So to use this feature, I have to turn on the critical load drop down. I'm just going to specify a critical energy %. And then I will also reduce our analysis period to 5 years just for faster simulation. And then we can see this survival function of the system on the right. This tells us that I have a 20% chance of surviving an outage that's greater than 4%, or that's greater than 4 hours. Whereas if I wanted to survive an outage for at least 8 hours, I've only got a 6% chance of doing that with my current system. We can also look at the other metrics by searching for resilience. So here we have the average critical load, the average max and min hours of autonomy. We can see the range of autonomous hours. So it's anywhere from 0 to 14, as well as the PDF, the CDF, and the survival function. And we have a time series, which states that if an outage had occurred at hour 10, my PV battery system would be able to meet my critical load for the next 8 hours. So now we'll touch briefly on how a user can fit their own battery system from manufacturer data sheets, scientific literature, or collected data. This graph here shows how some of the plots that I've shown before were used to fit the voltage model and also to fit the thermal model. And lifetime test models can also be used to fit the cycle lookup table. So I think in the interest of time, I won't go into this slide so that we can just do our last section of the updates and upcoming features to the battery model. We have the recent updates for an improved controller that results in a closer match with target battery power and a higher round-trip efficiency. We also have fixes to the thermal model and a cleaner interface. Upcoming features include default values for battery parameters for some chemistries, cycling as a function of temperature, resistance as a function of temperature, sub-minute battery simulations, which is available only through PySam or other SDKs, and also a new dispatch algorithm for behind-the-meter systems. So let me see. Okay, it looks like we have our results from REopt. It tells us that our optimal capacity is about 320 kilowatt hours and our optimal power is about 100. And it's going to ask if we can override our current system configuration. So now we have the custom battery power target generated by REopt. So now as I simulate this, it'll be interesting to look at the battery behavior. So now we see that our simple payback period has decreased to about 6.8 years. We can look at the battery profile. We see more variation in how much power it charges or discharges. Can also look at the relative capacity and see that it reaches about 77 after 25 years. And so that's an interesting feature that we've added. And so thanks everyone for your attention. I'll be happy to take any questions you may have. We received one during the registration process about battery performance for frequency regulation on second timescale from Fernando M. So I'll just start with this one. So in the SAM executable, the minimum time scale is 1 minute. However, we do have sub-minute battery modeling capability upcoming in our next release, but this will only be available through PySam or other SDKs. So I have an example Jupyter notebook of how this can be modeled for a battery. let's see. So this upcoming version of the battery model is imported as pysam.batteryStateful. It uses some parameters that are very familiar. We have the losses and replacements, the calendar and cycling fade parameters, as well as thermal and voltage and initial condition inputs. We have their size and our nominal bank voltage, as well as what chemistry we want. But now we can change the time step to be sub-minute. So here I've set it to be run on a second-by-second basis. And I would like to control this battery using power rather than current. So that's what this control mode of 1 is. So now I'm going to create a new instance of the battery and set up all of these parameters. Note I should also connect this battery to an inverter model to capture some efficiency losses at low input powers, which you might see for frequency regulation. Oops, I forgot to import. Here we go. So now we can just look at the state of the battery. The operating current is 0. We look at our max charging and discharge current, as well as our max charge and discharge power. See that our state of charge is 50%, and the battery is at the same temperature as the room, and it's currently at 550 volts. So now I need to generate some frequency regulation signal for a single hour. So here all I did was start with a sine wave with a period of 20 seconds and add some noise to it, and then center it around 0 so that the battery charge and discharge profile is also centered around 0. And now I'm going to use this signal as an input to the battery dispatch. I set the powers to this frequency regulation signal, and I'm just going to repeat this hour dispatch. So this is for 24 hours. And I'm going to look at what the capacity is over these 24 hours, as well as the difference between what the signal would like the battery to do and what the battery can actually do, and normalize that by all of my time steps. So when we run this, it will set the input power at every time step and do the execution. And then we can look at the power of the battery and see how well it matches our target power. And we'll also save the capacity, which is the Q max, so the maximum capacity divided by the nominal maximum capacity, which we saved in the beginning here. And so we see that over an hour, very little change in capacity. Well, you can still see some change in capacity, and we see that there's very little difference in the target. So our battery is able to follow the signal very well. So this is just an example, and you can connect this to the cash flow model if you wanted to run financial calculations, or or any other financial model. So are there any follow-up questions to this example?
Thanks, Teresa. Don't see any questions about this particular example, but there was a question about the thermal parameters, which is the heat transfer coefficient. I guess there's a default value of 20, H equals 20. And then the question is whether that is for a glycol cooling solution like the one in our Tesla battery.
Yeah, I don't really know what kind of liquid cooling a value of 20 for the heat transfer coefficient would be. I think you would have to do some, try to look that up.
Great. I'm not seeing any other questions. If there are any other questions, please type them in the questions window. We have a few more minutes left, so be happy to answer any other questions. There have been a couple already about recording of this webinar, and as I mentioned, we'll be posting those on the SAM website. You can go to the events page on the SAM website where you'll find the recordings for the most recent webinars. And then if you look at the navigation menu on the website, you'll see that there are videos pages for batteries and PV, the different financial models. And those there you'll find links to recordings of past webinars along with presentation slides and other supporting materials.
Yeah, I guess while I wait for questions, I can kind of go through the slide that I glossed over in case we didn't have time.
There are a couple of questions here. There's a question here, I guess, a question about, could you explain how this is applicable for the PAN world? Suresh, could you elaborate on that question? I'm not sure what you mean by PAN world. And then there's a question here about whether we foresee working on PV to grid applications. I guess that SAM's PV models are for grid connected systems, both behind the meter, in front of meter for power generations. So I think the answer is yes. Here's a question. Redox flow batteries going to higher load. Redox flow batteries going to higher load powers now. I guess the question is about modeling sort of recent designs in flow batteries in SAM.
Okay. I think our vanadium redox, our flow battery model was implemented just using these, using this model here, which is from 2015. And I don't know how this model compares in terms of its representation capability to maybe more recent models when it comes to modeling these more recent flow battery developments. And I don't think we have any tasks slated for updating this model. So yeah, I'm not really sure.
Okay. Yeah, if there's some particular configuration or type of battery that you're trying to model and having problems with or questions about, please let us know on the forum. Just go to the SAM website and go to the forum. You can post questions there and we can give you more detailed answers. There's a question here, is it possible to adapt the applied state federal incentives or to create custom incentives I can go ahead and take that one. So the incentives inputs page in SAM is sort of general enough to cover a wide range of incentives. There are some battery specific incentives that, you know, that a lot of the aspects of incentives that make them specific to a particular application have to do with capacity limits and you know, production limits and that sort of thing, or you know, whether the battery is charged only from the PV or only from the grid. And those kind of limits are SAM does not impose. So it's kind of up to you to, you can set up the incentive for a case, you know, where the system operates in such a way that it would qualify for the incentive. And then you have to look at the simulation results to see whether it violated any of those requirements, and then refine your design if it did. So there isn't a way to sort of to limit, you know, on the incentives page, there aren't check marks to say, you know, don't only allow the battery to charge from PV, for example, or only allow it to charge from the grid, or whatever the requirement might be. So you kind of have to do some iterative modeling to capture those, the way those incentives would actually work in a real project. All right, well, I think that's all the questions we have, and we are just a couple minutes over, so I think we can call it good. Thank you, Doris, for a great webinar today. And thank you to everyone for participating. And again, you can find a recording of the webinar along with links to the presentation slides on the SAM website. Thank you all. Have a great rest of your day, and we look forward to talking to you soon on the SAM forum or a future event. Goodbye.